Welcome to week 11, question 4, and here we're going to be looking at a method of optimizing a function when you have a constraint to consider in the business application. So here we have a function that's called the Lagrange function, and it helps us combine one function with another in order to solve and find maximum and minimum values. So I've put the Lagrange function up there with a little bit of an explanation, and let's see how it works in practice. So we have a question that says the total cost to produce X small clocks and Y large ones is given by this function. If a total of 36 clocks must be made, how should production be allocated so that total cost is minimized? So this is a very important statement. If a total of 36 clocks must be made, and we have X small clocks and Y large ones, we know that we have a constraint of X plus Y must equal 36. So we're going to put that there right away. What we need to do now is set up the Lagrange function. And if we look up here, we have the Lagrange function is X, Y, lambda. Lambda is a Lagrange multiplier, so it helps us combine these two functions, is equal to the original function, f at xy, minus lambda times the constraint function. Now the one thing we have to remember is we need to have the constraint function as a value of 0. So x plus y minus 36 equals 0. That's the form we need to have it in for this to work. So let's see what we have here. Okay, so this is technically our g at x function. Okay, so here we are. We have 7x squared plus 12xy plus 14y squared plus 10. It's a 10 minus lambda times x plus y minus 36. So we're going to multiply this through like this, through the bracket, and see what we have next. Minus lambda x minus lambda y plus lambda 36, or 36 lambda. Remember, this negative sign here has to apply over the terms in the bracket. So the next thing we need to do is find now 3 partial derivatives, one with respect to x, one with respect to y, and one with respect to lambda. We're going to do that, lambda, and we're going to do that on the next page. I've written the Lagrange function here for us to work with, and now we need to find the first derivatives with respect to each of the 3 variables. So let's find f sub x first, of x, y, lambda. And so remember, when we're taking partial derivatives, we are taking the derivative with respect to one of the variables, and we're considering the other variables as constants. So we're only looking for variables with an x in it, or a combination of x and another variable. So the first term we have 7x squared, so our derivative there will be 14x. We have 12xy, our derivative there will be 12y. And then we go along negative lambda x, so we just have negative lambda. We have, I'm going to put this down here because we're going to need some space in the middle. So the derivative with respect to y. So now we're keeping x and lambda as constants. So we have 12x would be our first derivative. That would be of the second term, plus 28y minus lambda. Okay, and our derivative with respect to lambda of xy lambda, so we're considering x and y as constants, we have negative x, negative y, positive 36. Okay, so those are our first derivatives, first partial derivatives, and we should be setting this equal to 0 next. And this one as well. And if we make these equations, now rearrange them for equaling lambda. So we have lambda equals 14x plus 12y, and here lambda equals 12x plus 28y. We now have two equations, each that equal lambda, so we can set those equal to each other and solve for x and solve for y. So we would do this, 14x plus 12y must equal 12x plus 28y. And I will take this to the next page and we'll solve it from there. So here are the two equations set equal to each other because they both equal lambda. Our next step would be collecting like terms. So we have 14x minus 12x would leave 2x on this side, and then 28y minus 12y would leave 16y on this side. And we can see that x equals 8y. So every x equals 8y. The next thing you would do, we want to find out what these actual values are. We're going to go back to the constraint function. You remember that we had x plus y equals 36. Small clocks, large clocks has to total 36. So now we have x as a value of y, so we can substitute 8y in for this x. So now we only have one variable, so we have 9y is equal to 36. So y must be equal to 4. And if we imagine y equaling 4, and the total of x and y have to be 36, we now have x plus 4 equals 36, so x must equal 32. So in order to minimize the cost, we would have to produce 32 small clocks and 4 large clocks. The last step is going to be trying to determine what that minimum cost will be at this production level. And we'll do that on the next page. Here we have the original cost function, and we know the values to minimize the cost are x equals 32, y equals 4. So we substitute those values into this cost function and solve. And again, paying attention to our order of operations. We have a value of 8,938, and that would be the minimum cost at this production level.